Hello, Sam here again. I'm going to be doing another Leetcode question, acting as a mock interview candidate. We'll do an easy one today. I'm still rusty, though starting to get a little bit more comfortable. We'll see if today's video is the same or if it proves me wrong. I'm going to choose one at random and I'll start a timer for it as well, which you can kind of see here in the bottom right. If you're interested in trying out the question as well, I'll have the link in the description, so feel free to follow along. I'm going to go into algorithms because I'm not trying to do any of the SQL stuff. I think that's interesting too, but not my goal today. Okay, so let's pick one at random and start the timer and see what we get. All right, we've gone number 258, add digits. So we're given an integer and repeatedly add all its digits until the result has only one digit and then return it. All right, that's kind of cool. Seems relatively straightforward at first. We're taking like the number 38, take the digits 3 and 8 and add them together. And we get the digit 11. Then we take those digits and add it together and we get 2. And eventually you get to, there's only one digit left, so we just return that. This is kind of interesting. I actually thought about, so there's a question of like, these are cycles. You're creating like sequences, or not cycles. There are sequences being formed based on your starting number. And a question is, does the number always end up with a single digit? And I think mathematically the answer is yes. They probably wouldn't be asking this otherwise. It has some similarities to the Fibonacci question we did last time, where you have a function call that essentially calls a subfunction for the other digits. So here, for example, the original function is 38 and then the subfunction is 11. And it just kind of keeps going through the sequence until you run out. Unlike the Fibonacci one where there's 2 calls per recursive call, which would be 2 to the k, this is just 1 to the k, 1 to the n, or sorry, just n essentially. Well, it's not n. I'm not actually sure what the big O is going to be of this. That's an interesting question. Well, let's start thinking about how we'd solve this problem first. Question number 1 is, how big could the input digit be? Is it being passed in as a string, or is it being passed in as an integer? There's kind of a couple of approaches we can get. So it looks like we're being passed in as an int. How big would the int be? Will it fit in memory? Will it be like int max int size? And the answer is yes, it's going to be max int, because let's say a 32-bit int, we have 1 digit less than that. So will you ever create an integer larger than the largest integer possible? And the answer is no, because every operation will always be reducing. Because if you had, like, say, 9 plus 9, you'd get 18, which is much smaller than 99. You can't ever create a larger digit, I think. Yeah, I think that's true. There's no way to create a digit larger. If there was, then we have kind of a diverging series. All right, that's kind of cool. So we know it's a converging series, which means it has a limit. Interested to see what that limit is. All right, input int is 2 to the 32 max minus 1. And comes as int. There's a couple of ways we can start thinking about this as we kind of talk it out loud. Approach one is do it string manipulation style, where you turn the int into a string, split it up into pieces, kind of use those individual bits and turn them back to ints and add them up again. Split string, int, and sum. Continue. I don't like this because the process of converting an integer to a string and back, while technically O of 1 is just feels kind of wasteful. I'll try to stop saying an interviewer might not like this approach just because it kind of offloads a lot of the work to the string manipulation standard libraries. I think that's a better way of putting it. Approach 2 is to sort of take the int and break into decimal 10 parts using modulo operators, or division with remainder. So for example, 38 modulo 10 is equal to 8. So then you can subtract 8 from 38 equals 30, and 8. That's one way to do it. If this was base 2, we could do it a different way. That's actually an interesting question. Does base 2, could we use base 2 binary type stuff? I can't really think of a way to do that right now, but that's an interesting question. There might be. all of these approaches right now are recursive, where you're taking these two bits, the 30 and the 8, and then the 30 divided by 10 gives you 3. You can do it something along those lines. So there's kind of two ways you can do this. 38 divided by 10, the int of that is going to be 3, as well as 38 modulo 10 is equal to 8. That gives us our 2 bits. And you kind of have to do this for any number that could be as big as, you know, a very large number. So you'll have to do kind of this in a for loop for each while, or a loop until empty. So there's some logic that we can approach there. And then after you've got all these digits and you sum them together, recursively call the function again. So that's kind of the approach I'm starting to think about right now. We can also ask the interviewer if they'd like us to do it, or if we're allowed to do it in string form, or if they'd prefer us to do it in an int form. The advantage of the string one is we don't have to think about modulo division and errors with that. The standard library kind of handles all that, because you could just take 38, give you 3 and 8, and then just, you know, sum those integers together. That's a choice. Also, we get 0, 0. So kind of an interesting question here also is, could we go the other way? And could we build, since we know the int is max int size, there's a limited number of values possible, technically, all of them. So 2 to 32. We could store all of them. So if space O of a 2 to 32 constant size is allowed, we could just memorize everything, calculate it all out and memorize it, and then O of 1 time complexity to pull it. That is one option. And 2 to 32 is actually not that big. So it would be stored. That's a good question. Actually, I'm not sure exactly how big that is, but gigs, megabytes, somewhere around megabytes to gigabytes, I think, is my guess. I might be entirely off on that. 2 to the power 32 is 4 bytes, kilobytes, megabytes. Yeah, 4.3 gigabytes. Which, I mean, it's a lot, but it's a one-time thing, and you could just memorize it all. Okay. Well, let's get started. I've been dallying around long enough. It's been about 8 to 9 minutes. Just trying to think of any other approaches. The main thing I was trying to think about is, can we calculate the sequence backwards somehow? Like, could we go from 0 to, 0 is always going to be 0. That's a cycle. But could we go from like 1 from, could we go to 2 to 1 plus 1? And then from that, could we get to 11 from 3 plus 8, and etc. And, you know, just build this up. And there's going to be a lot more than 3 plus 8. There'll probably be 2 plus 9, you know. You can do permutations of this. 1 plus 10 is not allowed. 4 plus 7, 5 plus 6. And so you could build up the permutations of all the possible, and it's a tree. Calculate the tree backwards somehow from these roots. Because the assumption is there's going to be a certain set of digits final outputs, there's actually going to be exactly 9 end nodes, 0 through 9. And maybe some of them aren't even reachable. I'm not too sure about that. I think they're all reachable in some form or fashion. But so if you have this tree, these 9 different trees, and they all grow out to all the possible digits inside the int, can we figure that out ahead of time mathematically? Probably the answer is yes. I don't know how to do it off the top of my head. So I just want to throw that out there for the interviewer, that we could probably spend time trying to figure that out. Okay, let's go back to approach 2 and just start getting to work and do the recursive approach, because I think that was the intent for this. So add digits, and our input is a num, and it's going to be an int, and our output will also be an int that is the num. We're guaranteed that the integer is legal and fits inside memory 2 to 32. So what we can just do is take the sum. We don't even need to. So one option was to break this up into a string of. So this could be like, let's say 1 2 3. Break it up into 1 2 3, and then sum them. But that stores O of k space for k digits in an int. And instead we can just go straight to summing without storing the integers in between. And that'll just bring us down to O of 1 space. And to do that, we don't actually care about the order we get the digits in. We can do it backwards. So what we can do is sum is 0, and then while the number, and since this passes as an int, it's its own value. It's not a pointer, at least in Python and most languages, C++ as well. While num exists, we take the sum plus the number modulo 10. So that gets that first digit, least digit. Then we take the number divided by 10, the number divided by 10, and we've just shifted it 1 over. And if this was in binary, you could do something like a binary shift over of 1, something along those lines. I think it's right shift or left shift. Not relevant, but that is one thing. If we were doing this in binary, it'd be technically a more efficient operation than this. Though most interpreters and compilers will make this pretty efficient. Either way, still O of 1. Still O of 1 with modern compilers. And it'll just keep moving the digit over while the number is greater than 0. So let's try 1 2 3. What'll it do? Let's actually keep it outside here. 1 2 3. So sum starts at 0. We'll take the sum plus the number modulo 10, which is equal to 3. So sum equals 3. Then number equals the int of 1 2 3 divided by 10, which becomes 12. Then we do it again. Sum plus 12 modulo 10, which is 2. So sum equals 5. And the num is equal to 12. And the reason I'm doing this is because I want to check the edge case at the end. And so far so good. And then finally we're at the last one, because num is 1 is still valid. So sum plus 1 modulo 10 equals 1. So sum equals 6. And num is equal to the int of 1 divided by 10, which is equal to 0, and that ends our list. And we have our final sum where we return it. Six, which in the case of 1 2 3, sum of that is equal to 6, so that is correct. If it was 0, what happens? While the number exists, it's 0, so it doesn't, so sum is just 0. That works just fine. I think we have a function that will work recursively here. Oh, right. This is just getting the sum of these digits. We don't return the sum directly. We're supposed to do the call while the digits is greater than. If num is less than 10, just return the number. So that's our final edge case, 0 through 9. Otherwise, we have to call this, return the add digits of num. That's the recursive call here. Yeah. So now, let's say in this case, 1, 2, 3, it calls add digits of 6, returns that, and 6 is less than 10, so it just returns 6. Whereas if it was 3 and 8, it would do 3 here and 8 there, it would get 11, add digits of 11, it would continue and do the loop until it got to 2. Okay. What is the time and space complexity for this? So we've established that the space complexity is O of 1, because we're not storing anything once we call the recursive call. We're just, we've used up all the digits here. We're just doing the recursive call directly. So nothing needs to get added into the stack. Are there loops higher up? I guess not. 2 plus 2 is 4. 8 plus 8 is 16. It all kind of comes down to some of the small digits. I don't know what the big O is for time. Time big O. What's a way we can think about this? Is it on average that the number of characters is the number of steps taken? I think it's a lot less than that actually, because you can have numbers that are, let's see, just 9. The biggest numbers I can think of, 99 gives you 18, because 9 plus 9 is 18, which gives you 9. So that's just 3. 999 gives you a larger number, 3 9s is 27, which is 9, which is also 3. That's interesting. 4 9s is, oh, I'm starting to wonder if this is logarithmic. 4 9s 36, I think. Yeah. And that's also 9. Kind of an interesting thing going on here, because you're basically just taking multiples of 9 for the largest digit. And we should be able to get one more with that. 45, and then 54, and it goes on. And these are all 3. So let's see. 9 9s 81. I think that's the largest one. 1 2 3 1 2 3 1 2 3 is 81, and that still gives you 9. How cool! You have to get a lot larger than that before you start getting numbers that are bigger. So what is that? So we know we're at least O of k for k digits in the int. And we're probably less than that. Probably less than O of k time. And integer-wise, we're definitely less than O of n. Definitely less than O of n. Because I can't think of any. This is the biggest number you can get with integers. And smaller numbers don't. In fact, you have to get to like past a billion before you start to get to a larger cycle. Is that true? Maybe if we go the other way. All right, before we get too far, we're about 19 minutes, and let's check if the code's correct. I'm sure you guys probably want to see that, and we can come back and try to solve it. So I did this all in a Google Doc, in case you hadn't noticed by now, because a lot of mock interviews or real interviews won't let you use an IDE. So it looks like num is the same here. And you need to kind of get practice with what you'll actually be using. I made a pretty silly skit the other day where I pretended to be a mentat, and that was kind of fun to pretend why you wouldn't use an IDE. And I don't know if you all have seen or read read the Butlerian Jihad, which is one of the prequels in the Dune series. And don't worry, no spoilers here, but it kind of goes into why machines and computers are not really used in the Dune movies and books. And it makes for an interesting setting. All right, so you got our loop. We got our main function here. If the number is less than 10, we just return it. We got our sum. Using the sum as the value is kind of maybe a little bit of a poo-poo because sum exists inside of the Python interpreter as a function that sums up values. So let's not do that. We could turn this into sort of a one-liner loop, but I don't think it would be any clearer, and it not really saves time. It doesn't really save time, so let's just keep it as is. Calls recursively, and yeah, let's see what we get. Hopefully I haven't missed any edge cases. Add digits. Add digits. My apologies, since this is inside of a class. Oh, number 38 returns 0. All right, what's the logic going on that we've done wrong? So our input's 38, which is not less than 10. While the number exists, which it does, total plus, oh, sorry guys, this was, there's a typo. I put in num instead of total, so it was just calling the value itself, and surprisingly did not go on an infinite loop, which is kind of weird. Well, let's try this again. Okay, passes for the first case and the second. Let's do a submission and see what we get. And it passes. All right, great to see. And even though it was recursive, surprised to see how fast it was. Again, this usually has nothing to do with the efficiency of the algorithm when it's a relatively simple problem. It has more to do with the Python interpreter and backend and whatever this is running on. But it is nice to see when it works. So let's talk about this one a little bit and still try to figure out what this big O is. I think that's an interesting question. We know it's less than O of n because the digits drop down really quickly. Let's try different digits. I just want to see. So 8, we did, what was it? 3 and 8, which gives us 11, which gives us 2. So that's a sequence of 3. Can we ever get a sequence larger than 3? Does this become O of like 1? There has to be. What's the largest digit you can get? We just got it there. So 2 to the power of 32 minus 1. So that's the largest digit. Two to the power 32 minus 1. So I know this looks like a lot, but it's just it's a pretty small number when it all comes together. So 11, 15. And 9 plus 6, 15 plus 7, 22, and 11 plus 5, 16. Let's add those as well. So 19, 22, 38, and then 40. That's actually, sorry, 38 plus 20 is 58, 57. So 57. And that just goes down to 5 plus 7 is... wow, after doing that last one, 12 and 3. So a cycle of 4. I mean, we're looking at close to O of 1, because I don't think you can get a larger digit than this. Well, you probably could get a larger sequence. There's fun math where if you have maybe more 9s in there, you get a bigger number, but we just established that if it was just the 9s, and you can't go bigger than this because that would be bigger than memory. So you'd have to do something like 4, 9, but you're not allowed. This is the largest digit that you can get with an int. You couldn't get something, you couldn't even do that because that'd be bigger than 2 to the 32 minus 1. So, I guess we actually are limited to a max of 4. How interesting. Largest digit is sequence of 4, so in the end, O of 1 time complexity, because you'll only ever have sequences between length 1 through 4. Correct me if I'm wrong. Please let me know in the comments if I'm missing something obvious. Maybe there's some interesting sequences that takes longer to converge. I'd love to know about that. But let me just put this in here for myself. one time. One space. One could argue, here's one thing we could do slightly differently, which is instead of doing a recursive call, could we do this? Because we're at what, 25 minutes? Let's say an extension is do this iteratively. And this is something I could easily see an interviewer doing. And it has some advantages because we're not entirely sure how the recursive call stores memory in stack. Is it keeping the total? Is it keeping like the previous digits? It might be. And in that case, we are storing 4 times as much data because it's only a sequence of 4 or so large. So it's actually not that big of a deal. But let's just say we want to do this iteratively so we are guaranteed and then we don't have to worry about that. We can say while the number let's say curry, or my curry equals num, or at the end num equals total, and then while num number is greater than equal to 10. So here, we're going to do the loop directly. And then we just return the number at the end. So we loop until the number is less than 10. Let's create a separate variable for this so we don't get confused by what it is. So there. So what's going on here is while the number is greater than or equal to 10, we create a copy of that number, and while that number, that current number is greater than 0, we'll keep summing up all the digits within it. Sum up all the digits. And then once that's done, we have our total for all the digits. We set the new number to that and continue the loop until we're done. So here, this loops until all of this is finished. So let's put that in here and see how that looks as well. And I'm just going to comment that out. And this stays outside of that loop. Okay, so just so you guys can see this also, here's the new code. Iterative approach, it'll loop until the number is greater than, while the number is greater than or equal to 10, it'll keep looping. And eventually it'll return that final num. So let's test it on the test cases. All right, seems to work still for those, and let's submit. And so this will be interesting. I'm going to see, yeah, see, even though this is a more efficient algorithm that uses less space overall than the first one, it takes longer, or it takes more time and uses more memory. And just shows that when you're talking about milliseconds on a test that's being run on the cloud, there's too much error or variance that you can't really take this into account unless people go way out of bounds for more complicated or less efficient algorithms. Either way, this is also really nice. I think it's good to be able to transition a recursive to an iterative approach. Hopefully this is interesting to y'all, and Let me know in the comments if you have any suggestions for, or please let me know if you know the big O for sure for this function and what the largest sequences are, or if there's a mathematical way to do that. Because I think that's kind of an interesting question. Being able to think about sequences that way is something that is definitely valued when you're trying to create optimized algorithms. All right, cheers and see you guys next time.